Welcome to Slumbertainment. Get comfortable, close your eyes, and let yourself relax. Tonight we explore the history of trains. Please like and subscribe for more restful content. Now, let's begin. Long before the first locomotive ever drew breath through its firebox, long before iron wheels pressed against iron rails, there existed a quieter dream in the minds of inventors and engineers. It was a dream born not of sudden inspiration, but of patient observation, of watching water boil in kettles, of seeing steam rise from heated vessels, of understanding that within this invisible vapour lay a force that might be harnessed, controlled, and set to work. The story of trains begins not with the thunder of engines across continents, but with this gentler contemplation of steam itself, with the gradual realization that heat and pressure, when properly contained and directed, could generate motion. In the centuries before locomotives, steam had already begun to reveal its possibilities. Ancient Greek mathematicians had toyed with steam-powered devices, creating curious toys and mechanisms that demonstrated the principle without pursuing its practical application. But it was in 18th century Britain, amid the coal mines and workshops of the Industrial Revolution, that steam power began its true emergence. The mines themselves created the need, for as shafts were driven deeper into the earth in search of coal and ore, water seeped in from surrounding rock, flooding the workings and threatening to halt extraction entirely. Pumping this water out by hand or by horse required enormous labour, and the deeper the mines went, the more impossible the task became. Thomas Newcomen, a humble ironmonger and Baptist preacher from Dartmouth, developed one of the first practical steam engines in 1712. His atmospheric engine was a massive, slow-moving contraption that used steam not directly for power, but to create a vacuum. Steam was admitted into a large cylinder, then cold water was sprayed inside to condense the steam, creating a partial vacuum that allowed atmospheric pressure to push down a piston. The piston's movement operated a rocking beam that could drive a pump. These engines were installed at mine heads throughout Britain, their great wooden beams rising and falling with methodical persistence, perhaps 6 or 8 strokes per minute, pulling water up from the flooded depths. They were inefficient, consuming vast quantities of coal to produce relatively little work, but they functioned, and in the context of a coal mine, where fuel was abundant, their inefficiency was tolerable. For decades, the Newcomen engine represented the state of the art in steam technology, and no one imagined these stationary pumping machines might one day move themselves. They were fixed installations, as permanent as the stone buildings that housed them, their cylinders and beams requiring solid foundations to contain the forces at work. The very idea of a moving steam engine seemed fantastical, a confusion of purpose. Yet within these unwieldy machines lay all the fundamental principles that would eventually propel locomotives. The conversion of heat into mechanical work, the use of a piston moving within a cylinder, the connection of that piston to mechanisms that could transfer motion elsewhere. The crucial transformation came through the work of James Watt, a Scottish instrument maker who in 1765 was asked to repair a model of a Newcomen engine. While working on this repair, Watt recognised the fundamental inefficiency in the design. The cylinder was repeatedly heated by incoming steam, then cooled by the water spray used to condense that steam, then heated again for the next cycle. This constant heating and cooling wasted enormous amounts of energy. Watt's insight was to add a separate condensing chamber, allowing the main cylinder to remain hot while condensation occurred elsewhere. This modification, along with numerous other improvements developed over the following years, transformed the steam engine from a crude pump into a sophisticated power source. Watt's engines were faster, more powerful, and dramatically more efficient than their predecessors, using perhaps 1/4 of the fuel for the same amount of work. With Watt's improvements, steam engines began to escape the confines of mineheads and appear in mills, factories, and workshops. They drove machinery for spinning cotton, grinding grain, and operating hammers. The rotative motion that Watt developed, using a sun and planet gear system to convert the back and forth movement of the piston into continuous rotation, made the engine adaptable to countless applications. Yet still, these were stationary engines, bolted to foundations, connected by shafts and belts to the machines they powered. The weight of the engine itself, the massive cast iron cylinders and beams, the brick chambers and chimneys, all suggested permanence rather than mobility. But a few curious minds began to wonder whether a steam engine might be made light enough and compact enough to move itself. The theoretical possibility was clear. If an engine could turn a wheel through rotative motion, why couldn't that wheel roll along the ground carrying the engine with it? The practical obstacles were substantial. The engines of Watt's era weighed many tons, required careful tending to maintain pressure and prevent explosions, and consumed prodigious amounts of fuel and water. Making such a device small enough to be self-propelling while retaining sufficient power to move its own weight seemed an impossible challenge. Yet in the closing years of the 18th century, several inventors began attempting precisely this impossible task, driven by the conviction that steam's potential had not yet been fully realized, that somewhere in the relationship between fire, water, pressure, and motion lay the possibility of something entirely new, something that might one day cross distances under its own power, something that would eventually be called a locomotive. The first attempts to create a self-moving steam engine were awkward, experimental affairs, more curiosities than practical machines. In 1769, a French military engineer named Nicolas-Joseph Cugnot constructed what many historians consider the first self-propelled mechanical vehicle. Cugnot's creation was designed to haul artillery for the French army, a massive tricycle-like contraption with an enormous copper boiler projecting from its front like the head of some mechanical beast. The boiler hung ahead of the single front wheel, which both steered and provided drive, creating an ungainly machine that was perpetually front-heavy and difficult to control. During trials in Paris, this steam wagon managed to lumber forward at perhaps 2 or 3 miles per hour, but it could only operate for 15 minutes before stopping to build up steam pressure again. On one demonstration, the machine crashed into a wall, earning the dubious distinction of being involved in the world's first motor vehicle accident. The French military, unimpressed by its performance, abandoned the project, and Cugnot's Fardier, as it was called, ended its days as a museum piece rather than the revolution in transport its creator had envisioned. Yet Cugnot's attempt, however flawed, proved that steam power could indeed propel a vehicle. The machine had moved under its own power, had carried its engine and fuel and water supply without external assistance. The problems were numerous, certainly, but they were problems of engineering rather than fundamental impossibility. Other inventors took note, particularly in Britain where steam engine development was most advanced, and where the practical mindset of the Industrial Revolution encouraged experimentation with mechanical solutions to transport challenges. William Murdoch, who worked as an assistant to James Watt, built a small model steam locomotive around 1784. This was a 3-wheeled vehicle, much smaller than Cugnot's artillery hauler, designed merely to demonstrate the principle rather than to carry loads. Murdoch tested his model on the roads near his home in Redruth, Cornwall, and on one evening trial the little machine reportedly escaped his control and went trundling down a lane on its own, frightening a passing clergyman who thought he was witnessing some kind of mobile demon. The incident was humorous, but it alarmed James Watt, who discouraged Murdoch from pursuing the idea further. Watt was protective of his steam engine patents, and worried that locomotive experiments might lead to dangerous high-pressure designs that could explode and bring disrepute to steam power generally. Under Watt's discouragement, Murdoch set aside his locomotive ambitions, though he kept the model throughout his life as evidence of what might have been. The true breakthrough in locomotive development required someone willing to work with high-pressure steam, something Watt had deliberately avoided in his own designs. The engines Watt built operated at pressures barely above atmospheric, using vacuum rather than pressure as their driving force. This made them safe and reliable, but also heavy and unsuitable for mobile applications. High-pressure steam, by contrast, could deliver much more power from a smaller, lighter engine, but it brought significant risks. Boilers could rupture explosively if pressure grew too high, or if the water level dropped too low, exposing heated metal to direct flame. Nevertheless, the potential advantages were too compelling for some inventors to ignore. Richard Trevithick, a mining engineer from Cornwall, grew up surrounded by steam engines. The Cornish mines where he worked were among the deepest in Britain, and pumping engines were essential to their operation. Trevithick was a large, physically powerful man with an intuitive understanding of mechanics and a willingness to take risks that more cautious engineers avoided. In the 1790s, he began experimenting with high-pressure steam engines that were much smaller and lighter than the low-pressure engines of Watt's design. By 1800, Trevithick had built a high-pressure engine compact enough to mount on a wheeled vehicle. On Christmas Eve of that year, 1800, he demonstrated his puffing devil on the roads of Camborne in Cornwall, carrying several passengers uphill at 4 miles per hour. The machine worked, astonishing onlookers with its power and mobility, but after the demonstration, Trevithick and his companions retired to a nearby inn to celebrate. They left the engine unattended with its fire still lit, and the water in the boiler eventually boiled away, causing the machine to overheat and catch fire, destroying itself while the inventors celebrated inside. Undeterred by this setback, Trevithick built another road locomotive in 1803, which he brought to London for demonstration. This machine, called the London Steam Carriage, successfully operated on the streets of the capital, carrying passengers through the city and proving that steam locomotives were not merely theoretical possibilities, but working realities. Yet the roads of the time were poorly suited to heavy vehicles. The steam carriage frequently broke through the road surface, and the jarring, uncomfortable ride discouraged potential passengers. Moreover, the machine was expensive to operate, and Trevithick found no investors willing to finance its commercial development. After these demonstrations, he began to consider that perhaps roads were not the ideal surface for steam locomotives. Perhaps what was needed was a smoother, more regular path, something specifically designed to support the weight and guide the motion of these powerful machines. Perhaps what was needed was rails. Rails themselves were not a new invention when Trevithick turned his attention to them. For centuries, mines had used wooden rails to guide wheeled carts, creating smooth pathways along which horses could pull much heavier loads than they could manage on rough ground. The principle was simple. A wheel rolling on a rail encounters far less resistance than a wheel rolling on dirt or cobblestone. The rail provides a hard, even surface that doesn't sink or deform under weight, and the flanged wheels that ran on these rails were guided by the track itself, requiring no steering. In the coal mines of northeastern England, wooden rails had been in use since the 1600s, allowing horses to haul loaded coal wagons from the pithead to the nearest river or seaport. Over time, these wooden rails were capped with iron straps to reduce wear, and eventually the rails themselves were cast entirely from iron, creating the first true iron railways. By the early 1800s, these horse-drawn railways were common throughout Britain's mining districts. The rails were typically laid as parallel tracks with a gauge, or width between rails, that varied from place to place depending on local practice and the size of the wagons used. Some lines used flanged wheels running on flat rails, while others used plain wheels running on L-shaped rails, where the vertical face of the L kept the wheels on track. These wagonways, as they were called, stretched for miles across the countryside, linking mines to canals and rivers, their wooden sleepers and iron rails creating permanent corridors of transport. Horses plodded along these routes day after day, pulling trains of connected wagons, and the efficiency of this system was already well established. A single horse on rails could pull a load that would require a team of horses on an ordinary road. Richard Trevithick recognised that these existing railways provided the perfect testing ground for his steam locomotives. The rails would support the weight of his engines without breaking through as roads did, and the smooth surface would allow the locomotive's power to be used efficiently for pulling loads, rather than overcoming road resistance. In 1804, Trevithick was commissioned to build a locomotive for the Penydarren Ironworks in South Wales. The ironworks owner, Samuel Homfray, had made a bet with a rival that a steam locomotive could haul 10 tons of iron along the tramway that connected the ironworks to the Glamorganshire Canal, a distance of nearly 10 miles. Trevithick's locomotive would either win this bet or prove that steam traction on rails was impractical. The Penydarren locomotive that Trevithick constructed was a remarkable machine, the first true railway locomotive in history. It featured a single horizontal cylinder that drove a large flywheel, which in turn drove the wheels through gears. The boiler was cylindrical, with the firebox at one end and a chimney at the other, and the exhaust steam was directed up the chimney to increase the draft through the fire, making it burn more intensely. This technique of using exhaust steam to strengthen the fire was one of Trevithick's innovations, and it would become a standard feature of steam locomotives for the next century and a half. The entire machine weighed about 5 tons and rode on 4 wheels, though only the rear axle was driven by the engine. The wheels had smooth rims without flanges, relying on the L-shaped cast iron tramway plates to keep them on track. On February 13, 1804, Trevithick's locomotive made its historic journey. With Trevithick himself at the controls, the engine pulled 5 wagons loaded with 10 tons of iron and 70 men who had climbed aboard to witness the event. The locomotive successfully hauled this load the entire distance from Penydarren to the canal basin, travelling at about 5 miles per hour, completing the journey in 4 hours and 5 minutes including stops. It was a triumph of engineering, the first time a steam locomotive had successfully hauled a load on rails, and it won Samuel Homfray his bet. The locomotive had proven its capability, demonstrated that steam power could replace horsepower on railways, and shown that the future of overland transport might be very different from the past. Yet despite this success, the Penydarren locomotive was not put into regular service. The problem was not with the locomotive itself, but with the tramway it ran on. The rails had been designed for horse-drawn wagons, and the weight of the locomotive repeatedly broke the brittle cast iron plates. After a few more trial runs, the locomotive was removed from the rails and set up as a stationary engine at the ironworks, where it spent the rest of its working life driving a hammer. Trevithick's locomotive had succeeded technically, but had revealed a crucial limitation. Railways would need to be built much stronger if they were to support locomotives regularly. The existing infrastructure of horse tramways, laid down over decades, was simply not robust enough for these powerful new machines. Trevithick built other locomotives over the following years, including one called Catch Me Who Can, that he demonstrated to the public in London in 1808. he constructed a circular track in a field near what is now Euston Square and charged spectators £1 to ride behind the locomotive as it circled the track at 12 miles per hour. For several weeks, Londoners came to see this marvel, this machine that propelled itself without horses. But again, Trevithick found no investors willing to finance commercial development. The technology was proven, the capability was demonstrated, but the business case remained elusive. After this final attempt, Trevithick turned his attention to other projects, eventually leaving England to work on mining ventures in South America. He would die in poverty in 1833, largely forgotten, never seeing the vast railway networks that would one day cover the world using the principles he had pioneered. After Trevithick's pioneering work, locomotive development entered a period of quiet experimentation. The fundamental concept had been proven, the essential mechanics demonstrated, but the practical application remained elusive. Various engineers in the coalfields of northeastern England continued to refine the idea, building locomotives for specific industrial purposes, trying different configurations of cylinders and wheels, testing various approaches to converting steam pressure into rotative motion. These were working machines rather than demonstrations, employed at collieries and ironworks where their performance could be evaluated under real conditions over extended periods. They laboured in relative obscurity, watched only by miners and engineers rather than paying spectators, their successes and failures recorded in the practical ledgers of industrial enterprises rather than in public newspapers. One of the most significant figures in this developmental period was William Hedley, the viewer or chief engineer at Wylam Colliery, near Newcastle upon Tyne. Wylam had a wooden railed tramway connecting its coal pits to the River Tyne several miles away from the bay, and the cost of feeding the horses that pulled coal wagons along this tramway was substantial. In 1812, Hedley decided to investigate whether a locomotive might be more economical than horses. There was considerable doubt at the time about whether smooth iron wheels on smooth iron rails could gain sufficient grip to pull a load, or whether the wheels would simply spin uselessly. Some engineers believed that locomotives would need to propel themselves by pushing against the ground with legs like a mechanical horse, or by gripping a toothed rail with a cogwheel, or by some other mechanism that didn't rely on simple friction between wheel and rail. To settle this question, Hedley constructed a curious experimental carriage that could be pushed along the rails by men walking alongside it. By measuring how much force was required to move this carriage and comparing it to the weight on the wheels, Hedley determined that friction alone would indeed be sufficient, provided the locomotive was heavy enough to press its wheels firmly against the rails. This discovery was crucial because it meant locomotives could be relatively simple machines without complex gripping mechanisms. Armed with this knowledge, Hedley designed and built a locomotive that entered service at Wylam in 1813. This machine, which came to be known as Puffing Billy, was an ungainly contraption with a tall chimney, a cylindrical boiler mounted on a framework of beams, and two vertical cylinders that drove the wheels through an arrangement of beams and connecting rods that looked rather like the walking beam of a stationary engine turned on its side. Puffing Billy was not elegant, but it worked reliably, hauling coal wagons day after day along the wooden rails of the Wylam tramway. The locomotive proved that steam traction could be practical and economical for industrial transport, that these machines could work continuously without the rest and feeding that horses required, and that despite their initial cost, they could pay for themselves through sustained service. When the Wylam tramway was eventually relaid with iron rails, Puffing Billy continued in service, and indeed it worked for nearly 50 years before finally being retired in 1862. Today it survives in the Science Museum in London, one of the oldest locomotives in existence, its mechanical components still clearly showing Hedley's approach to solving the problems of steam traction. While Hedley worked at Wylam, another engineer was developing locomotives at Killingworth Colliery, just a few miles away. George Stephenson had been born in 1781 in a small cottage beside the Wylam tramway, the son of a fireman who tended the pumping engine at a local colliery. Stephenson grew up in poverty, unable to attend school, teaching himself to read as a young man by attending evening classes after his shifts at the colliery. He worked his way up from engine tender to engine wright, becoming responsible for maintaining and repairing the stationary steam engines that pumped water from the coal pits. By 1812, he was the engine wright at Killingworth, and he began to consider whether locomotives might be built to haul coal from the pits. In 1814, Stephenson built his first locomotive, Blücher, named after the Prussian general who had recently helped defeat Napoleon. This machine incorporated several improvements over earlier designs. Stephenson used direct connection between the pistons and the wheel cranks rather than the complex system of beams and levers that Hedley had employed, making the mechanism simpler and more efficient. He also connected the wheels on each side of the locomotive with chains, ensuring that all wheels turned together and provided driving force. Blücher could haul 30 tons up a slight gradient at 4 miles per hour, and while this was no faster than horses could manage, the locomotive could work continuously and didn't require rest or feeding. Over the next several years, Stephenson built more locomotives for Killingworth and other collieries, steadily refining the design. He experimented with different arrangements of cylinders and wheels, tested various ways of connecting the driving wheels together, and developed improved springs to help the locomotive cope with irregularities in the track. In 1815, he patented a design that used steam blast in the chimney to increase the draft through the fire, reinventing the technique that Trevithick had used years earlier, but which had not become widely known. This steam blast was essential to making locomotives powerful and efficient, allowing them to generate high temperatures in a relatively small firebox and produce steam quickly enough to sustain continuous operation. By the early 1820s, Stephenson had become the most experienced locomotive builder in Britain, having constructed more engines and accumulated more practical knowledge than any other engineer. He had learned through direct experience which designs worked reliably and which failed, which materials could withstand the stresses involved and which could not, which dimensions and proportions produced the best balance of power and efficiency. This practical expertise, gained through years of patient refinement and careful observation, would prove invaluable as the age of railways began to dawn. The colliery locomotives of northeastern England, working in obscurity, hauling coal from pit to port, had become sophisticated and reliable machines, ready to expand beyond their industrial origins and begin a transformation of transport that would reshape the world. The transition from colliery locomotives to public railways required more than technical capability. It demanded vision, capital, and a willingness to challenge the established order of transport. Britain in the early 1820s was a nation crisscrossed by canals, those artificial waterways that had been dug with immense labour over the previous half-century to connect industrial centres with ports and markets. The canal system had revolutionised the movement of heavy goods, making it possible to transport coal, iron, and manufactured products in quantities that would have been impossible by road. Canal companies were wealthy and powerful, their shareholders enjoying steady returns on their investments, and they had little interest in seeing their monopoly challenged by any new form of transport. Yet the very success of industrialisation was creating demands that the canal system struggled to meet, and nowhere was this more apparent than in the connection between the textile manufacturing centre of Manchester and the port of Liverpool. Manchester's cotton mills were consuming raw cotton arriving from America and India through Liverpool. then sending finished cloth back through the same port for export to markets around the world. The volume of this trade was enormous and growing, but the Bridgewater Canal and other waterways connecting the two cities were slow, frequently congested, and subject to winter freezing. The journey by canal took days, and the charges levied by the canal companies were substantial. A group of Manchester merchants began to consider whether a railway might offer an alternative, a faster and more reliable connection that could break the canal monopoly and reduce their transport costs. What they envisioned was not a mere colliery tramway with a single locomotive hauling coal, but a proper railway line with multiple trains, regular schedules, and service open to any paying customer. It would be the first true railway in the modern sense, a common carrier operating between two major cities. The merchants formed a company, raised capital through share subscriptions, and sought an Act of Parliament to authorise construction of the Liverpool and Manchester Railway. This process took several years and faced fierce opposition from canal companies and landowners whose property would be crossed by the line. 3 attempts to pass the necessary legislation failed before Parliament finally granted approval in 1826. The route would run for 31 miles across challenging terrain that included deep cuttings through rock, embankments across marshland, a tunnel under Liverpool, and a crossing of Chat Moss, a vast bog that many engineers considered impassable. The estimated cost was approaching £500,000, an immense sum, and there was no certainty that locomotives could reliably haul trains across such distances, or that the public would choose to travel by this untested means of transport. The railway company's board of directors appointed George Stephenson as the chief engineer for the project. It was an enormous responsibility and a vindication of Stephenson's years of patient work in the collieries. He would be responsible not merely for building locomotives, but for surveying and constructing the entire railway line, solving all the engineering problems that arose, and proving that this ambitious venture could succeed. Stephenson approached the work with characteristic determination, though his lack of formal education sometimes worked against him. When he appeared before parliamentary committees to defend the railway's proposals, his Northumbrian accent and straightforward manner were mocked by educated gentlemen who doubted that a man of his background could accomplish what he claimed. Yet Stephenson understood locomotives and railways more deeply than any of his critics, and he persevered despite their condescension. The construction of the Liverpool and Manchester Railway required engineering work on a scale unprecedented for a railway. Through the town of Olive Mount on the approach to Liverpool, the line had to pass through a cutting that reached 70 feet deep in places, requiring the excavation of hundreds of thousands of cubic yards of rock. Workers with pickaxes and explosives laboriously removed the stone, which was then loaded into horse-drawn carts and taken away. At Chat Moss, the railway had to cross 4 miles of bogland, where the peat was sometimes 30 feet deep and so soft that men and horses would sink into it. Stephenson's solution was to lay the railway on a floating foundation of timber and brushwood, essentially creating a raft that spread the weight across the surface of the bog. Skeptics predicted the entire construction would simply sink and disappear, but Stephenson's approach succeeded, and the line crossed Chat Moss safely. As construction progressed, the railway company had to decide what form of power would be used to move trains along the completed line. Some directors favoured stationary steam engines placed at intervals along the route, hauling trains between stations using cables, a system already used on some steep inclines. Others wondered whether horses might still be more practical than locomotives. To settle the question, the directors announced a competition to be held in October 1829 at Rainhill, a village along the partly completed railway. The competition would test locomotives under controlled conditions, and the winning design would be purchased by the railway company and used as the model for engines ordered for the line. The Rainhill trials, as this competition came to be known, would determine the future of railway locomotion and demonstrate to the world whether steam locomotives were truly ready to enter regular passenger service. The requirements for the competition were specific and demanding. Locomotives had to weigh no more than 6 tons, haul 3 times their own weight at a minimum speed of 10 miles per hour, consume their own smoke to minimise pollution, and have a steam pressure not exceeding 50 pounds per square inch to ensure safety. Each locomotive would be required to run back and forth over a measured section of track multiple times, covering a total distance equivalent to a return trip between Liverpool and Manchester, and would be judged on speed, reliability, and fuel consumption. 5 locomotives were entered in the competition, though only 3 were completed in time to participate. Among them was an engine built by George Stephenson and his son Robert, an engine they had named Rocket, and which embodied several crucial innovations that would define steam locomotive design for decades to come. The trials were about to reveal whether the age of railways had truly arrived. The Rainhill trials began on October 6, 1829, and drew enormous crowds of spectators who came from across the region to witness this contest between machines. The stretch of track chosen for the trials was a level straight section about 1.5 miles long, with grandstands erected for dignitaries and viewing areas marked out for the public. The atmosphere was festive, almost like a country fair, with vendors selling food and drink, and people dressed in their finest clothes, treating the event as both entertainment and a glimpse into the future. Among the spectators were engineers and investors, newspaper reporters, and curious citizens, all eager to see whether these iron horses could perform as their builders claimed. The first locomotive to be tested was Novelty, built by John Ericsson and John Braithwaite. It was a lightweight, elegant machine that looked more like a carriage than the industrial engines of the collieries. Novelty featured a vertical boiler and could reach impressive speeds, delighting the crowd by accelerating quickly and running smoothly. The spectators cheered as it flew past, faster than any locomotive they had seen before, and many assumed it would be the winner. However, Novelty's lightweight construction proved to be its weakness. During the repeated runs required by the competition, the boiler developed leaks and mechanical parts began to fail. The locomotive spent more time being repaired than running, and eventually it had to withdraw from the competition without completing the required distance. The second serious contender was Sans Pareil, built by Timothy Hackworth, who was the locomotive superintendent at the Stockton and Darlington Railway. Sans Pareil was a solid, powerful engine built along more traditional lines, and it performed reliably during its initial runs. However, it was heavier than the competition rules allowed, and this extra weight told against it. Moreover, during one of its runs, a cylinder cracked, ending its participation. The locomotive had demonstrated capability, but had not completed the full requirements of the trials. This left Rocket, the Stephenson engine, as the only locomotive to complete the full trial successfully. Rocket incorporated several innovative features that set it apart from earlier designs. Most significantly, it featured a multi-tubular boiler, with 25 copper tubes running through the boiler from the firebox to the chimney. Previous locomotives had used a single large flue to carry hot gases through the boiler, but Rocket's multiple small tubes provided much more surface area for heat transfer, allowing the boiler to generate steam far more efficiently. This design had been suggested by Henry Booth, the treasurer of the Liverpool and Manchester Railway, and Robert Stephenson had implemented it brilliantly. The result was a locomotive that could produce steam quickly enough to sustain high speeds continuously. Rocket also featured cylinders mounted at an angle rather than vertically, with direct connection to the driving wheels through connecting rods. The driving wheels themselves were relatively large, allowing for higher speeds, while smaller carrying wheels supported the front of the locomotive. The firebox was separate from the boiler barrel, positioned at the rear where the fireman could easily tend it, and the exhaust steam was directed up the chimney to create a strong draft through the fire. Every aspect of Rocket's design had been considered carefully, each element working in harmony with the others to create a machine that was powerful, efficient, and reliable. During the trials, Rocket performed magnificently. It hauled its required load back and forth along the measured track, completing run after run without mechanical failure, maintaining speeds above 10 miles per hour and reaching as high as 30 miles per hour during one demonstration. The crowd watched in amazement as the locomotive accelerated smoothly, climbed slight gradients without difficulty, and responded quickly to the controls. The rhythmic beat of its exhaust, the white plume of steam from its chimney, and the steady churning of its wheels created a spectacle that was both impressive and strangely beautiful. Here was a machine that moved with purpose and power, that could sustain its effort hour after hour, that represented a fundamental advance in human capability. When the trials concluded on October 14th, Rocket was declared the winner, having been the only locomotive to complete all requirements. The judges awarded George and Robert Stevenson the prize of £500, and more importantly, Rocket had proven the viability of steam locomotion for regular railway service. The design principles embodied in Rocket, particularly the multi-tubular boiler and the direct drive to the wheels, became the foundation for virtually all subsequent steam locomotive development. Engineers would refine these principles, enlarge the scale, and add sophistication, but the essential form had been established. The modern steam locomotive had been born at Rainhill, and the railway age could now begin in earnest. The Liverpool and Manchester Railway opened for regular service on September 15th, 1830. The opening day was attended by the Duke of Wellington, the Prime Minister, and other dignitaries who travelled from Liverpool toward Manchester in a ceremonial train hauled by Rocket's sister locomotive, Northumbrian. The day was marked by triumph, but also by tragedy. During a stop at Parkside, William Huskisson, a Member of Parliament and prominent supporter of the railway, stepped down from his carriage and was struck by Rocket, which was approaching on an adjacent track. Huskisson's leg was crushed, and despite being rushed to medical attention by Northumbrian in the first emergency use of a railway, he died that evening from his injuries. He became the first notable casualty of the railway age, a sobering reminder that these powerful machines brought dangers as well as benefits. Despite this tragedy, the railway's opening demonstrated conclusively that steam trains could provide regular, reliable transport between cities. Within weeks, the Liverpool and Manchester Railway was carrying thousands of passengers and vast quantities of freight. The journey that had taken days by canal now took hours by rail. The service was faster than stagecoaches, more reliable than canals, and cheaper than either alternative for many types of goods. The railway was an immediate commercial success, and investors took notice. If a railway could be profitable connecting Liverpool and Manchester, why not between other cities as well? Within months, proposals for new railways were being drafted across Britain, each seeking to replicate the success of the Liverpool and Manchester line. The railway age had arrived, and the world was about to be transformed by iron rails and steam power. The success of the Liverpool and Manchester Railway ignited what can only be described as railway fever throughout Britain. In the early 1830s, dozens of railway schemes were proposed, each seeking parliamentary approval and investor capital to connect towns and cities that had previously relied on canals, turnpike roads, and coastal shipping. The potential profits seemed limitless, and speculators rushed to purchase shares in railway companies, often before a single rail had been laid, or even before the necessary acts of Parliament had been secured. Some of these schemes were carefully planned and economically sound, while others were wildly optimistic or outright fraudulent, but all contributed to a sense that the nation stood on the threshold of a transportation revolution. The construction of these early railways followed patterns established by the Liverpool and Manchester line, but on an ever-expanding scale. Thousands of labourers, known as navvies, after the navigators who had dug the canals a generation earlier, moved across the countryside excavating cuttings, building embankments and laying track. These men worked with pickaxes, shovels and wheelbarrows, shifting earth and rock through sheer physical effort, living in temporary camps that followed the advancing construction. The work was brutal and dangerous, with frequent accidents from rockfalls, explosions and collapsing excavations, yet the wages were good by the standards of the time, and the navvies developed a fierce pride in their labour and their ability to transform landscapes. The engineering challenges varied with each new line. The London and Birmingham Railway, authorised in 1833 and opened in 1838, required extensive earthworks including the massive Kilsby Tunnel, which ran for over a mile through treacherous ground that proved far more difficult to excavate than anticipated. Quicksand was encountered, flooding the workings repeatedly, and 13 stationary steam engines had to pump water continuously for 8 months before the tunnel could be completed. The cost overruns were substantial, but when finished, the railway provided a direct connection between the capital and the industrial Midlands, shrinking the journey time from days to a matter of hours. The Great Western Railway, championed by the brilliant engineer Isambard Kingdom Brunel, took a different approach to railway construction. Brunel was convinced that broader gauge track would allow for larger, more stable locomotives and smoother running at higher speeds. While most railways were built to a gauge of 4 feet 8.5 inches, a measurement inherited somewhat arbitrarily from the early colliery tramways, Brunel specified a gauge of 7 feet for the Great Western. His vision was of a railway that would be superior in every respect, with gentle gradients, sweeping curves, and stations designed as architectural statements. The line from London to Bristol, authorised in 1835 and gradually opened through the late 1830s, featured some of the finest engineering of the early railway age, including the Box Tunnel near Bath, which at nearly 2 miles was the longest railway tunnel in the world at the time of its completion. As railways spread, locomotive design continued to evolve. Robert Stephenson, who had become one of the leading locomotive builders in Britain, developed increasingly sophisticated engines for the various railways under construction. His locomotives grew larger and more powerful, with bigger boilers, additional driving wheels, and improved mechanical arrangements. The basic principles established with Rocket remained, but every dimension was carefully refined through experience. Other builders emerged as well, establishing workshops in Newcastle, Manchester, and other industrial centres, each contributing innovations and competing for orders from the multiplying railway companies. The railways quickly revealed advantages that went beyond simple transport efficiency. The mail, previously carried by stagecoach at considerable expense and limited speed, could now be moved by train much faster and more reliably. The Royal Mail contracted with railway companies to carry post, and special mail carriages were developed with facilities for sorting letters while in transit, so that mail could be organised during the journey and distributed immediately upon arrival. The impact on communication was profound, effectively shrinking the nation as information could flow more rapidly between distant places. Passenger travel was transformed even more dramatically. The early railways offered different classes of accommodation, from luxurious first-class carriages with upholstered seats and windows to Spartan third-class cars that were often little more than open wagons with benches. Yet even third-class travel by rail was faster and often cheaper than stagecoach travel had been, and working people could now contemplate journeys that would previously have been impossible. The concept of the excursion train emerged, with special services offered at reduced fares to allow people to visit the seaside, attend sporting events, or simply explore parts of the country they had never seen. In 1841, Thomas Cook organised what is considered the first package tour, chartering a special train to carry temperance supporters from Leicester to a rally in Loughborough, and this venture led to the development of the organised tourism industry. The railways also began to standardise time itself across Britain. Previously, each town had kept its own local time based on the sun's position, so that noon in Bristol occurred several minutes after noon in London. This variation had been tolerable when communication was slow, but railway timetables required a unified time system. Gradually, all towns adopted London time, transmitted along the railway telegraph lines that were being strung alongside the tracks. This railway time became the standard, eventually adopted nationally, and the railways had imposed a temporal uniformity across the country to match the physical connections they had created. By the mid-1840s, Britain had over 2,000 miles of railway in operation, with more under construction. The network was beginning to take coherent form, with major cities connected and branch lines extending into smaller towns. The investment required had been enormous, consuming capital that might otherwise have gone into canals, turnpikes, or overseas ventures, but the returns were becoming evident. Goods moved faster and cheaper, industries had access to larger markets, cities could draw food from a wider agricultural hinterland, and people possessed a mobility that previous generations could scarcely have imagined. The social and economic effects rippled outward, touching nearly every aspect of life, and it was becoming clear that the railway was not simply a new form of transport, but a force that would reshape society itself. The iron rails stretching across the landscape carried more than passengers and freight. They carried the future, and that future was arriving faster than anyone had anticipated. As Britain's railway network expanded through the 1840s, other nations watched with a mixture of admiration and determination to build their own systems. The advantages of railways were too obvious to ignore, and the technology, while sophisticated, was not so complex that it could not be replicated. Engineers and investors from across Europe and North America travelled to Britain to study the railways in operation, to purchase locomotives from British manufacturers, and to recruit experienced British engineers who could supervise construction in their home countries. The export of railway technology became a significant British industry, with locomotives, rails, and expertise flowing outward to seed railway networks across the world. In the United States, railway development proceeded along paths shaped by the vast distances and dispersed population of the young nation. The first common carrier railway in America, the Baltimore and Ohio, began construction in 1828, the same year the Liverpool and Manchester Railway was being built across the Atlantic. The Baltimore and Ohio faced different challenges than British railways, with longer distances between major cities, less capital available for construction, and terrain that ranged from coastal plains to mountain ranges. American engineers adapted railway technology to these conditions, building lighter track on wooden ties rather than stone blocks, designing locomotives with swivelling front wheels to navigate sharper curves, and generally favouring pragmatic solutions that reduced initial costs, even if they resulted in rougher riding or lower maximum speeds. The early American locomotives often looked quite different from their British counterparts. While British engines tended to be compact and heavy, built for the relatively short distances, and substantial engineering works of British railways, American locomotives developed a distinctive appearance with large cowcatchers mounted on the front to clear obstacles from the track, prominent headlights for night running, and tall balloon-shaped smokestacks fitted with spark arresters to prevent line-side fires. These features reflected the operating environment, where railways often ran through unsettled country with unfenced rights of way, where livestock might wander onto the tracks, and where wooden bridges and trestles made fire a constant concern. One of the most influential American locomotive designers was Matthias Baldwin, a Philadelphia jeweler and toolmaker who built his first locomotive, Old Ironsides, in 1832. Baldwin's engines incorporated rugged construction and practical features suited to American conditions, and his works in Philadelphia became one of the leading locomotive manufacturers in the world, eventually producing thousands of engines over the following century. The Baldwin locomotive, with its characteristically American appearance and emphasis on power and reliability over refinement, became an export product itself, shipped to railways in South America, Asia, and other developing regions where conditions resembled those of the American frontier. In continental Europe, railway development proceeded more systematically, often with greater government involvement than in Britain or America. Belgium, having achieved independence in 1830, immediately began building a state-owned railway network as a matter of national policy, seeing railways as essential infrastructure for economic development and national unity. The Belgian state railways, opened from 1835 onward, were carefully planned with the capital Brussels at the centre and lines radiating to the major cities and neighbouring countries. This planned approach contrasted with the more chaotic development in Britain, where competing private companies had built lines according to commercial opportunity rather than national strategy. Germany, still divided into numerous independent states, saw railway construction proceed state by state, though often with coordination between neighbouring territories. The first German railway, a short line from Nuremberg to Fürth, opened in 1835, used a locomotive imported from Britain and named Adler, or Eagle. Within a decade, railways were spreading across the German states, built to slightly different standards and gauges in different regions, but gradually forming a network. The strategic importance of railways for moving troops and supplies was recognised early by German military planners, and this influenced railway policy, ensuring that trunk lines connected major cities and that bridges and tunnels were built strongly enough to carry heavy loads. The railways would play a crucial role in German unification decades later, both as physical connections between the states and as economic arteries that made unified governance more practical. France approached railway construction with characteristic centralisation, adopting a plan in 1842 that designated Paris as the hub with 6 main lines, radiating outward like spokes to the frontiers and major ports. The French railways combined private capital with government oversight, and the engineering standards were high, with substantial masonry viaducts and tunnels wherever necessary to maintain gentle gradients and easy curves. French locomotive design evolved somewhat independently, with engineers at manufacturers like Schneider developing machines suited to the operating characteristics of French railways and the preferences of French engineers, who favoured certain arrangements of wheels and cylinders that differed from British practice. Russia presented perhaps the greatest railway challenge due to its immense distances and harsh climate. The first Russian railway, opened in 1837, was a short line from St. Petersburg to the imperial residence at Tsarskoye Selo, built partly as a curiosity for the aristocracy, but the potential of railways to bind together the vast Russian Empire was obvious, and in 1842 Tsar Nicholas I approved plans for a major railway connecting St. Petersburg to Moscow. This line, over 400 miles long, would be built to a gauge of 5 feet, broader than standard European gauge, partly for strategic reasons to make it difficult for invading forces to use Russian railways if captured. The construction took a decade and required substantial foreign expertise, but when opened in 1851, it demonstrated that railways could function even in the severe Russian winter, provided that engines and infrastructure were built robustly enough. In each country, railways adapted to local conditions while retaining the fundamental technologies pioneered in Britain: the steam locomotive, the iron rail, the essential relationship between wheel and track. These remained constant, but everything else varied according to available resources, terrain, climate, and social organisation. What was emerging was not a single global railway system, but rather a family of related systems, each bearing the imprint of its particular circumstances, yet all connected by shared principles and, increasingly, by international traffic as railways reached borders and required agreements about through running, standardised equipment, and coordinated schedules. The railway was becoming a universal technology, adapted to serve the particular needs of each nation, while simultaneously creating connections that transcended national boundaries. By the 1850s, the railway had matured from experimental novelty to established technology, and locomotive design had advanced considerably from the simple machines of the pioneering years. Engineers now understood through accumulated experience which configurations of cylinders, wheels and boilers produced the best performance for different types of service. The classification of locomotives by their wheel arrangement became standardized, providing a shorthand way to describe a locomotive's design and intended purpose. A locomotive with 4 small leading wheels, 4 large driving wheels and 2 trailing wheels would be described as a 4-4-2, and this designation immediately conveyed information about the machine's likely capabilities and the sort of work for which it was designed. The front wheels, often smaller and mounted on a swivelling truck or bogie, helped guide the locomotive into curves and provided stability at speed. The driving wheels, connected directly to the cylinders and powered by steam, were sized according to the intended service. Large driving wheels, 6 feet in diameter or more, allowed for high speeds because each revolution carried the locomotive farther along the track, but they provided less pulling power for starting heavy trains or climbing gradients. Smaller driving wheels, perhaps 4 or 5 feet in diameter, gave greater mechanical advantage and better pulling power, but limited maximum speed. Trailing wheels supported the weight of the firebox at the rear of the locomotive and allowed for a larger firebox that could generate more steam. The art of locomotive design lay in balancing these elements to create a machine optimized for its intended work. Passenger locomotives tended toward large driving wheels and elegant proportions, built for speed and smooth running on well-maintained main lines between major cities. These engines pulled trains of comfortable carriages at speeds that would have seemed miraculous just decades earlier, sustaining 50 or 60 miles per hour over long distances and maintaining schedules with increasing reliability. The passengers, seated in compartments with upholstered benches and large windows, could watch the landscape flow past at unprecedented velocity, seeing countryside that would have taken days to traverse by coach pass in mere hours. The sensation of railway travel became familiar. The rhythmic clicking of wheels over rail joints, the swaying motion, the occasional whistle, all combining into an experience that defined modernity. Freight locomotives, by contrast, were built for power rather than speed. They featured smaller driving wheels, often with multiple pairs coupled together to multiply the adhesive weight available for pulling heavy loads. These engines hauled long trains of goods wagons, moving coal from mines to cities, agricultural products from farms to markets, manufactured goods from factories to ports. The economic impact of cheap, reliable freight transport was profound, allowing industries to source raw materials from greater distances and to serve larger markets, encouraging specialisation and economies of scale that had been impossible when transport costs were high. Some railways began to experiment with locomotives that could burn coal more efficiently and produce less smoke, an increasingly important consideration as trains passed through populated areas. The firebox design evolved to ensure more complete combustion, and various patents were taken out for special arrangements of bricks and baffles within the firebox that improved the mixing of air and fuel. The quality of coal itself varied considerably, with some types producing more heat and less clinker than others, and locomotive designers had to consider what fuel would typically be available on the railways where their engines would operate. Water presented another significant consideration in locomotive operation. Steam locomotives consumed water voraciously, converting it to steam that was then exhausted through the chimney and lost. A locomotive working hard might use hundreds of gallons per hour, and railways had to establish water towers at regular intervals where locomotives could replenish their supplies. The water crane became a familiar sight at railway stations, a tall standpipe with a swinging arm that could be positioned over the locomotive's tank while the fireman operated a valve to fill it. The quality of water varied, and hard water with high mineral content could cause scale to form inside the boiler, reducing its efficiency and eventually requiring the locomotive to be taken out of service for cleaning and maintenance. The workshops where locomotives were built and maintained became substantial industrial complexes, employing hundreds or thousands of workers with specialised skills. The crew works of the London and North Western Railway, the Swindon works of the Great Western Railway, and similar establishments at Derby, Doncaster and other railway towns became centres of engineering excellence, where locomotives were not only repaired but designed and constructed from raw materials. These works had their own foundries for casting iron and brass, forges for shaping steel, machine shops equipped with lathes and planers and drilling machines, and erecting shops where components were assembled into complete locomotives. The workers in these shops developed deep knowledge of locomotive construction, knowledge that was passed from master craftsmen to apprentices through practical training rather than formal education. Each railway company developed its own design preferences and operating practices, creating distinctive families of locomotives that reflected the philosophy of the company's chief mechanical engineer. On the Great Western Railway, the locomotives retained Brunel's broad gauge and developed unique characteristics under a succession of talented engineers. On the London and North Western Railway, locomotives were painted in a distinctive black livery and built to exacting standards at Crewe. The Midland Railway favoured elegant passenger engines painted in a rich crimson lake, while the Great Northern Railway produced powerful locomotives with a characteristic bottle green finish. These differences created variety and fostered healthy competition, as each railway sought to demonstrate the superiority of its practices through the performance of its trains. The locomotive crews themselves, the drivers and firemen who operated these machines, developed considerable skill and took pride in their work. The driver controlled the locomotive's speed and operation, managing the regulator that admitted steam to the cylinders and the brake that could slow or stop the train. The fireman maintained the fire in the firebox, shoveling coal at the right moments to keep steam pressure steady, monitoring the water level in the boiler, and watching for any signs of mechanical problems. Working together in the confined cab of a locomotive, often for hours at a time in all weathers, driver and fireman formed close partnerships, developing an intuitive understanding of their particular engine and how to coax the best performance from it. They learned to interpret subtle sounds and vibrations that indicated how well the engine was running, to anticipate when additional steam would be needed for a climb or when the fire needed building up, and to handle the machine with a combination of technical knowledge and practical instinct that could not be taught from books alone. As railway networks expanded and traffic increased through the 1850s and 60s, safety became an ever more pressing concern. The early railways had operated with relatively simple systems for controlling train movements, often relying on time intervals between trains and the vigilance of station staff to prevent collisions. A train would depart a station, and a specified period would elapse before the next train was permitted to follow on the same track. This system worked adequately when traffic was light and trains ran infrequently, but as railways grew busier, the limitations and dangers became apparent. Trains did not always maintain their schedules, and a delayed train might find itself being overtaken by a faster service following behind, or two trains might enter the same section of single track from opposite directions with catastrophic results. The electric telegraph, which had been developed independently of railways but found its most important early application alongside them, provided the means for safer train control. Telegraph wires were strung on poles beside the railway tracks, connecting stations and signal boxes, allowing near instantaneous communication over distances that would take trains many minutes to traverse. Station masters could now confirm that a train had arrived safely before permitting the next train to depart, and signalmen controlling junctions could verify that the route was clear before allowing a train to proceed. The telegraph transformed railway operation from a system based on time and assumption to one based on confirmed information and positive control. Signalling systems evolved in parallel with telegraph communication. The earliest signals were often simple flags or boards displayed by railway policemen stationed along the line, but these were replaced by fixed signals mounted on posts beside the track. Initially, these signals used rotating boards that showed different aspects by day and coloured lights by night, but gradually the semaphore signal became standard, with an arm that could be raised or lowered to indicate whether the line ahead was clear or occupied. A horizontal arm meant danger, requiring the train to stop, while a lowered arm indicated the line was clear and the train could proceed. These signals were visible from considerable distances, giving locomotive drivers adequate warning to stop their trains if necessary. The problem of stopping trains reliably was itself a significant challenge. Early locomotives and carriages were equipped only with simple brakes operated by hand, with the locomotive crew able to apply brakes on the engine's wheels and guards in brake vans at the rear of the train able to screw down brakes on their vehicles. The rest of the train had no brakes at all, relying on friction and the weight of the vehicles to resist motion once the locomotive ceased pulling. This arrangement was marginally adequate for slow-moving trains, but became increasingly dangerous as speeds increased. A fast-moving train might require many hundreds of yards to stop, and if an unexpected obstacle appeared on the line or a signal was missed, there was little that could be done to prevent a collision. Various inventors developed systems for communicating brake application throughout the length of a train, but the most successful approach proved to be the continuous automatic air brake developed by George Westinghouse in the United States during the 1860s. Westinghouse's system used compressed air in a pipe running the length of the train, with each vehicle equipped with a brake cylinder that would apply brakes when air pressure was reduced. The crucial innovation was making the system fail-safe. If the train separated accidentally, breaking the air pipe, the loss of pressure would automatically apply the brakes throughout the train rather than leaving vehicles to run freely. This automatic feature made the system inherently safe, as any failure of the system resulted in braking rather than loss of braking capability. The adoption of continuous brakes was gradual, as it required retrofitting existing rolling stock and training staff in the new systems. But by the 1880s, most major railways had equipped their passenger trains with some form of continuous brake. whether Westinghouse's air brake or alternative systems using vacuum rather than compressed air. The impact on safety was profound, as trains could now be stopped far more quickly and reliably, and drivers had confidence that applying the brake would bring the entire train under control, rather than just the locomotive and brake van. Block signalling systems emerged as the standard method for managing train movements safely. The railway line was divided into sections or blocks, and only one train was permitted in any block at a time. The signals at the entrance to each block were controlled by signalmen in signal boxes, who communicated by telegraph with adjacent boxes to establish which blocks were occupied and which were clear. Before allowing a train to enter a block, the signalman would obtain permission from the next box ahead, confirming that the previous train had cleared the block. This system of positive control, with mechanical interlocking to prevent conflicting signals from being displayed, and rules requiring strict adherence to signalling indications, reduced accidents dramatically and allowed railways to operate multiple trains safely on the same tracks. The signal boxes themselves became complex mechanical installations, housing frames of levers that controlled points and signals through systems of wires and rods. A large junction might require a signal box with dozens or even hundreds of levers, each precisely labelled and arranged according to the layout it controlled. The signalman's skill lay in understanding the traffic patterns, knowing which routes to set for approaching trains, and working efficiently to keep traffic moving while maintaining absolute safety. The mechanical interlocking ensured that points could not be moved under a standing train, and that conflicting signals could not be cleared simultaneously, but it was the signalman's judgment and experience that kept the railway functioning smoothly. Accidents still occurred, of course, despite these safety systems. Human error, mechanical failure, poor visibility in fog, or simple bad luck could still lead to collisions or derailments. Each significant accident was investigated thoroughly, and the lessons learned led to further improvements in equipment and procedures. The Board of Trade, which regulated Britain's railways, maintained detailed accident statistics and issued recommendations that became mandatory requirements. Similar regulatory bodies in other countries performed comparable functions, gradually building a body of safety regulations that made railways far safer than any previous form of transport. The public's perception of railway safety evolved over time as well. Early railway travel had seemed frighteningly dangerous to people accustomed to the slower pace of horse-drawn vehicles, and any accident received prominent newspaper coverage. But as railways matured and safety systems improved, the statistics demonstrated that travelling by train was actually remarkably safe compared to travelling by road or sea. Millions of passengers made railway journeys every year, and the vast majority arrived at their destinations without incident. The railway became not only a familiar part of daily life, but a trusted one, and this trust was built on the careful accumulation of safety measures, each learned through experience and implemented with the understanding that the railway's greatest responsibility was to deliver its passengers and freight safely to their destinations. The locomotives of the late 19th century grew steadily larger and more powerful as engineers pushed the boundaries of what steam technology could achieve. The fundamental principles remained those established decades earlier: the multi-tubular boiler, the direct drive from cylinders to wheels, the use of exhaust steam to create draft through the fire, but every dimension expanded as railways demanded greater capacity and higher speeds. Boilers grew longer and wider, carrying more water and providing more heating surface. Fireboxes increased in size, allowing for fiercer fires that could generate steam more rapidly. Cylinders grew in diameter, capturing more energy from each charge of steam. Driving wheels multiplied, with locomotives featuring not just one pair of driven wheels, but 2 or 3 or even 4 pairs, all coupled together with connecting rods to combine their adhesive weight and pulling power. The compound locomotive represented one attempt to extract more work from steam by using it twice. In a compound engine, high-pressure steam from the boiler entered a small high-pressure cylinder where it expanded and did work. Then instead of being exhausted to atmosphere, this partially expanded steam was directed to a larger low-pressure cylinder where it expanded further and did additional work before finally being exhausted. This arrangement extracted more energy from each pound of steam, improving fuel efficiency, though it added mechanical complexity. Compound locomotives were widely adopted in continental Europe, particularly in France, where the engineer Alfred de Glaën developed elegant designs with 4 cylinders arranged in a configuration that balanced the forces beautifully and provided smooth, powerful operation. British railways experimented with compounding, but generally preferred the simplicity of conventional 2-cylinder simple expansion engines, accepting slightly lower efficiency in exchange for easier maintenance. The development of superheating in the early 20th century provided another significant improvement in locomotive efficiency. Superheating involved passing steam from the boiler through additional tubes exposed to hot gases in the smoke box, heating the steam well above its boiling point and drying it completely. This superheated steam contained more energy and could be used more efficiently in the cylinders, extracting more work without requiring higher boiler pressure. Superheated locomotives could haul heavier trains or maintain higher speeds using the same amount of fuel and water as conventional saturated steam locomotives, and the technology was gradually adopted across most railways worldwide. The visible sign of a superheated locomotive was often a slightly different arrangement of pipes and a header visible near the front of the boiler, though to passengers the only noticeable difference was that these engines performed their work with greater ease. Speed became an increasingly important measure of railway prestige and capability. Express passenger trains began to cover distances at average speeds above 60 miles per hour, with maximum speeds reaching 80 or even 90 miles per hour on favourable stretches of track. These speeds required not only powerful locomotives, but also careful attention to track quality, curve geometry, and train weight. The permanent way, as the track structure was called, had to be maintained to exacting standards, with rails firmly secured to sleepers and ballast properly distributed to provide stable support. Curves were banked or canted so that the outer rail was slightly higher than the inner, allowing trains to lean naturally into the curve and reducing the sideways forces on passengers. Signal spacing had to account for the longer distances required to stop fast-moving trains, and drivers needed clear visibility far ahead to observe signals and potential hazards in time to react. The fastest trains became sources of national pride, with railways competing to offer the quickest journey times between major cities. The race to Scotland between England's east and west coast routes in the 1890s saw trains covering the distance from London to Edinburgh or Aberdeen at unprecedented speeds, with special lightweight trains hauled by the finest locomotives and crewed by the most experienced drivers. These races were ultimately curtailed by agreement among the companies involved, as the intense competition was judged to compromise safety, but they demonstrated the capabilities of late Victorian railway engineering and captured public imagination in ways that more mundane freight or local passenger services could not. Freight locomotives evolved along different lines, prioritizing pulling power over speed. These engines featured smaller driving wheels to maximize their mechanical advantage, and they often had 6 or 8 or even 10 coupled driving wheels to provide sufficient adhesive weight for starting heavy trains. A freight locomotive might haul a train weighing hundreds or even thousands of tons, its multiple driving wheels gripping the rails as the engine worked up to speed, exhaust beats coming in rapid succession as the cylinders drove the wheels around. Once moving, the train's momentum helped carry it forward, but starting from rest or climbing gradients required sustained maximum effort from the locomotive, with the fireman shoveling coal steadily into the firebox to maintain steam pressure, and the driver carefully controlling the steam admission to prevent wheel slip. Tank locomotives, which carried their water and coal supplies in tanks and bunkers, mounted directly on the locomotive frame rather than in a separate tender, became common for shorter distance work and branch line services. These engines were self-contained and could run equally well in either direction without needing to be turned around, making them ideal for push-pull operation on branch lines and for shunting work in yards and industrial sidings. Tank locomotives ranged from tiny engines with just 4 wheels that worked in factories and docks, up to substantial machines with multiple coupled driving wheels that handled suburban passenger services or freight collection duties. Specialised locomotives appeared for particular tasks and conditions. Banking engines stationed at the foot of steep gradients provided additional power to help heavy trains climb, coupling onto the rear of the train and pushing while the train locomotive pulled from the front. These engines were built for maximum power rather than speed, with small driving wheels and massive boilers capable of generating enormous quantities of steam for the intense effort of climbing gradients. Mountain railways in Switzerland, Austria, and other alpine regions developed locomotives equipped with rack and pinion mechanisms, where a toothed wheel on the locomotive engaged with a toothed rail laid between the running rails, allowing trains to climb gradients far steeper than would be possible relying on the wheel-rail adhesion alone. Some railways in tropical regions developed locomotives with enclosed cabs to protect crews from intense heat and monsoon rains, while railways in extremely cold climates fitted snowplows and equipped locomotives with features to prevent water and lubricating oil from freezing. By the early 20th century, the steam locomotive had reached a high level of sophistication and specialization. Hundreds of different designs existed, each optimized for particular conditions and requirements, but all sharing the fundamental characteristics that had emerged from decades of accumulated experience. The steam locomotive had become mature technology, refined and reliable, capable of performing an enormous range of tasks, from hauling express passenger trains at high speed to moving vast quantities of freight across continents. The golden age of steam was at hand, though few suspected that within half a century, new forms of motive power would begin to challenge steam's supremacy. While steam locomotives continued to evolve and dominate railway operations into the 20th century, alternative forms of motive power had been under investigation for decades. The limitations of steam were well understood by engineers. The inefficiency of converting heat to mechanical work through the intermediate step of generating steam, the constant need for water and fuel, the labour required to prepare and maintain locomotives, and the environmental nuisance of smoke and cinders. As early as the 1830s, inventors had experimented with battery-powered electric motors on small demonstration railways, though the batteries of that era were far too heavy and weak to provide practical motive power. The real breakthrough in electric traction came with the development of the dynamo in the 1860s and 70s, which made it possible to generate electricity efficiently and to transmit it through wires to motors that could drive railway vehicles. The first successful electric railway opened in 1879 at the Berlin Industrial Exhibition, where Werner von Siemens demonstrated a small locomotive hauling passenger cars around an oval track. The locomotive drew current from a third rail laid between the running rails, powering an electric motor that drove the wheels. The demonstration proved the principle, though the tiny scale and exhibition setting meant it remained more curiosity than serious transport. Over the following years, electric tramways began to appear in cities, replacing horse-drawn trams with vehicles that drew power from overhead wires and could carry passengers more efficiently through crowded streets. These urban electric railways demonstrated that electric traction was practical and economical for relatively short distances with frequent stops, though extending the technology to mainline railways presented greater challenges. The City and South London Railway, opened in 1890, became the world's first deep-level electric underground railway, tunnelling beneath the streets of London with electric locomotives hauling trains of windowless carriages through tube tunnels, too narrow and confined for steam operation. The locomotives were small, ungainly-looking machines with their motors and control equipment enclosed in streamlined casings, drawing power from a third rail and operating in the clean, smoke-free environment that electric traction made possible. The railway proved successful enough that it pioneered the development of London's extensive underground system, all of which would eventually operate with electric traction. Mainline electrification proceeded more cautiously, as it required enormous capital investment to string overhead wires or install third rails along hundreds of miles of track, and to build power stations capable of supplying the necessary electricity. The first significant mainline electrification was completed by the Baltimore and Ohio Railroad in 1895 through a long tunnel under Baltimore, where smoke from steam locomotives had made conditions unbearable. Electric locomotives handled trains through the tunnel, while steam locomotives continued to operate on the open line at either end. This arrangement demonstrated that electric and steam traction could coexist on the same railway, with each used where it offered advantages. Switzerland and other alpine countries embraced electrification enthusiastically in the early 20th century, as their mountainous terrain with steep gradients and numerous tunnels made smoke from steam locomotives particularly problematic, while abundant hydroelectric power from mountain rivers made electricity relatively cheap. The Swiss railways gradually electrified their network, developing powerful electric locomotives that could haul heavy trains up steep mountain grades with a sustained effort that would have challenged even the largest steam locomotives. Electric locomotives had the advantage of drawing power from stationary power stations rather than generating it on board, which meant they could be simpler and lighter than steam locomotives of equivalent power. Moreover, electric motors provided high torque at low speeds, making them excellent for starting heavy trains and climbing gradients. The overhead wire system, where locomotives drew current from suspended cables through spring-loaded pantographs mounted on the locomotive roof, became the standard for mainline electrification in most of Europe. Different countries adopted different voltages and frequencies for their electrical systems, reflecting independent development and different engineering traditions, though this created complications where electrified railways crossed borders. A locomotive designed for the French system operating at 25,000 volts, alternating current could not run on the Belgian system using 3,000 volts direct current without substantial modifications or complete replacement at the frontier. In parallel with electric traction development, another alternative to steam was emerging in the form of the internal combustion engine. Gasoline and diesel engines, developed in the late 19th century for stationary and marine applications, offered the possibility of self-contained motive power without the complexity and infrastructure requirements of steam or electric systems. Early petrol-engined rail cars appeared in the early 1900s, though the limited power of these engines restricted them to light passenger services on branch lines. The diesel engine, with its greater efficiency and power density, showed more promise for railway application, and in the 1920s, several manufacturers began producing diesel-powered locomotives and rail cars. The diesel locomotive faced a significant technical challenge in transmitting power from the engine to the wheels. Diesel engines, unlike steam engines, could not start under load and required a transmission system to allow the engine to run at its most efficient speed while the locomotive accelerated from rest. Early diesel locomotives used mechanical transmissions similar to those in trucks and buses, but these were complex, prone to wear, and limited in the power they could handle. The breakthrough came with diesel-electric transmission, where the diesel engine drove an electrical generator, and electric motors mounted on the axles drove the wheels. This arrangement allowed the diesel engine to run at constant optimal speed, while the electric motors provided infinitely variable speed and high starting torque. The diesel-electric locomotive combined the advantages of diesel power, self-contained fuel supply, and no need for external infrastructure, with the excellent traction characteristics of electric drive. Germany led early diesel locomotive development, with manufacturers producing powerful diesel-electric engines in the 1930s that could match the performance of steam locomotives on express passenger services. These early diesel locomotives were not yet economically competitive with steam or electric traction in most applications, but they demonstrated the potential of the technology. In the United States, where coal was abundant but labour costs were rising and railways faced increasing competition from road and air transport, diesel locomotives began to appear attractive as a means of reducing operating costs. General Motors, through its electromotive division, developed standardized diesel-electric locomotives that could be mass-produced and maintained efficiently, and during the 1940s and 50s, American railways dieselized rapidly, retiring steam locomotives wholesale and transforming their operations around diesel power. The variety of motive power systems in use by mid-century created a patchwork of technologies across the world's railways. Steam remained dominant in many countries, particularly where coal was cheap and labour for maintaining locomotives was abundant. Electric traction prevailed in densely trafficked areas and mountainous regions, where the infrastructure investment could be justified. Diesel-electric locomotives found favour where flexibility and freedom from fixed infrastructure were valued, and where the economic case for dieselisation could be made. The choice of motive power reflected not just technical considerations, but economic circumstances, national resources, labour costs, traffic patterns, and historical development paths, and there was no single correct answer that applied universally. The age of motive power diversity had arrived, and railways around the world operated with whichever technology best suited their particular situation. Among the vast family of locomotives that evolved during the steam era, certain designs departed dramatically from conventional practice, representing either bold experiments or specialized solutions to unusual problems. These unconventional machines, though often few in number and sometimes short-lived, demonstrated the creativity and ingenuity of railway engineers willing to challenge accepted wisdom and explore alternative approaches. Some of these unusual locomotives succeeded admirably in their intended roles, while others proved impractical or unnecessary, but all contributed to the rich tapestry of railway history and expanded understanding of what was possible with rail-borne motive power. The Fairlie locomotive, developed by Robert Fairlie in the 1860s, featured a double-ended design with two boilers joined back-to-back and sharing a single firebox in the middle. Each boiler drove a separate power bogie beneath it, with the bogies able to swivel independently to negotiate curves. This arrangement gave the Fairlie locomotive extraordinary flexibility, allowing it to traverse sharp curves that would defeat conventional locomotives, while providing double the power of a single boilered engine of similar size. The fireman stood in the central cab between the two boilers, tending a double-sided firebox and monitoring two sets of gauges. Fairlie locomotives found favour on narrow-gauge railways in mountainous regions, particularly in Wales and Mexico, where their ability to negotiate tight curves proved invaluable. The Festiniog Railway in North Wales operated Fairlie locomotives successfully for over a century, with some engines still in occasional service today, testament to the soundness of the basic design. The Garrett locomotive represented another approach to creating a powerful yet flexible engine for difficult routes. Herbert Garrett's design, patented in 1907, placed the boiler on a cradle suspended between two separate engine units, with each unit consisting of a powered bogie, fuel and water tanks, and cylinders. The engine units could pivot independently beneath the boiler, giving the locomotive excellent curve negotiating ability despite its great length and power. The Garrett's design allowed for a very large boiler, as the boiler itself did not have to fit within the loading gauge and was carried high above the wheels, and the water and fuel tanks positioned over the driven wheels increased adhesive weight where it was most needed. Garrett locomotives were built in enormous numbers for railways in Africa, Australia, and other regions, where sharp curves, steep gradients, and limited infrastructure demanded maximum power from minimum track standards. Some Garrett locomotives were truly massive machines, with multiple pairs of driving wheels on each engine unit, capable of hauling trains of great weight up mountain grades at respectable speeds. The Shea locomotive, developed by Ephraim Shea in the 1870s for American logging railways, abandoned the conventional arrangement of cylinders driving wheels directly through connecting rods. Instead, the Shea featured vertical cylinders mounted on one side of the boiler, driving a shaft that ran along the side of the locomotive. This shaft transmitted power through bevel gears to all the wheels, which were mounted on swivelling bogies. The result was a locomotive that could negotiate appallingly rough track, including temporary logging railways laid directly on the ground with minimal preparation, and that could climb astonishingly steep grades through the use of very low gearing. Shea locomotives were slow, their top speed rarely exceeding 15 miles per hour, but they were immensely powerful for their size and could operate reliably in conditions that would destroy conventional locomotives. The distinctive sound of a Shea at work, with its syncopated exhaust beat and the clanking of gears and drive shafts, was unmistakable, and these engines became synonymous with mountain logging operations across North America. Turbine locomotives represented attempts to harness the efficiency of steam turbines for railway service. Unlike reciprocating engines with their back and forth piston motion, steam turbines extracted energy from steam as it flowed through carefully shaped blades, converting pressure directly into rotary motion. Turbines could be much more efficient than reciprocating engines, particularly at high power outputs, but they operated best at high rotational speeds, tens of thousands of revolutions per minute, while locomotive wheels needed to rotate at a few hundred revolutions per minute at most. This mismatch required complex reduction gearing, adding weight and mechanical complication. Several railways experimented with steam turbine locomotives in the 1920s through 1950s, including the London, Midland and Scottish Railway, which built a turbine locomotive that entered regular service on express passenger trains. These machines were smooth-running and powerful, but the mechanical complexity and maintenance requirements generally outweighed the efficiency gains, particularly as diesel and electric locomotives were becoming available as alternatives to steam. The experimental high-speed steam locomotives built in various countries during the 1930s represented the ultimate expression of conventional steam technology pushed to its limits. The London and North Eastern Railway's Mallard, streamlined and carefully engineered for minimum air resistance, achieved 126 miles per hour in 1938, a speed record for steam locomotives that has never been broken. German, American, and French railways built similar high-speed streamlined locomotives, their bodies enclosed in smooth casings that hid the traditional mechanical components and gave them a sleek, modern appearance. These locomotives demonstrated that steam power could compete with emerging diesel and electric technologies for speed, though the specialized nature of high-speed running and the intensive maintenance required meant these engines were not practical for widespread adoption, Rack railways, designed for extremely steep gradients in mountainous terrain, employed a toothed rail laid between the running rails, with the locomotive carrying one or more toothed wheels that engaged this rack. On the gentlest gradients, the locomotive could rely on normal wheel rail adhesion, but when grades exceeded about 1 in 14, the risk of wheel slip became too great, and the rack engagement provided positive drive. Various rack systems were developed, with different tooth profiles and engagement mechanisms, each with advantages for particular conditions. The apt system, widely used in Switzerland and elsewhere, used parallel toothed rails with the teeth offset, so that the locomotive's pinion wheels always had engagement. Rack railways could climb gradients as steep as 1 in 4 or even steeper, hauling trains of passengers to mountain summits that would be impossible to reach with conventional adhesion railways. Cable-operated inclines represented the extreme end of steep-grade railway operation, used where even rack railways were impractical. On these systems, stationary steam engines at the top of the incline wound cables that hauled trains up and lowered them down, with the descending train's weight often assisting in hauling the ascending train up the other cable. The Linton and Lynmouth Cliff Railway in England operated on this principle, though using water balance rather than a steam engine, with water tanks in each car that could be filled or emptied to control which car descended and which ascended. Industrial inclines used similar principles to haul coal or ore from mines in mountainous terrain, creating railways that were essentially vertical or near-vertical transport systems, more akin to elevators than conventional railways, yet still using wheeled vehicles running on rails. Monorails, suspended railways, and other unconventional track configurations represented attempts to reduce construction costs or overcome specific geographical obstacles. The Wuppertal-Schwebebahn in Germany, opened in 1901, suspended its cars from an overhead track that followed the valley of the Wupper River, creating a railway that required minimal ground-level right-of-way and could snake through the city above the river and streets. This elevated suspended railway continues in operation today, carrying millions of passengers annually and demonstrating that unconventional railway configurations could be practical for specific applications. Various monorail systems were built in different countries, some with cars riding atop a single rail, others with cars suspended beneath, each claiming advantages over conventional twin-rail configurations, though none achieved widespread adoption beyond specialised tourist or urban transit applications. The decades following the Second World War witnessed a fundamental transformation in railway operations across much of the world, as steam locomotives gave way to diesel and electric traction. This transition was driven by practical economic considerations rather than nostalgia or tradition. Steam locomotives, for all their proven capability and the deep knowledge accumulated about their operation, required substantial labour and infrastructure to maintain. Each engine needed daily preparation before service, with fires lit hours before departure to raise steam, boilers filled with water, and mechanical components inspected and lubricated. At the end of each day's work, the locomotive required cleaning, ash removal and servicing. Depots needed coal storage facilities, water towers, ash pits, and specialised equipment for boiler washing and mechanical repairs. The skilled labour force required to maintain a fleet of steam locomotives was substantial, and as wages rose in the post-war period, these labour costs became increasingly burdensome. Diesel locomotives offered a stark contrast in operational simplicity. A diesel engine could be started within minutes and was ready for service almost immediately. It required no external fuel or water supply beyond its onboard tanks, which could be refilled quickly at any convenient location. Maintenance, while still necessary, was less frequent and could be performed by mechanics with automotive rather than specialized steam experience. Most significantly, diesel locomotives were far more efficient in their use of fuel energy. Where a steam locomotive might convert only 6 or 7% of the heat energy in its coal into useful work at the wheels, with the remainder lost through radiation, incomplete combustion, and the inherent thermodynamic limitations of the steam cycle, a diesel-electric locomotive could achieve efficiencies of 25 or 30%. This meant that despite diesel fuel being more expensive per unit of energy than coal, the overall operating costs could be lower, particularly when labour savings were included. The dieselisation of North American railways proceeded with remarkable speed during the 1940s and 50s. The major locomotive builders, particularly General Motors through its electromotive division and the American Locomotive Company, produced standardised diesel-electric locomotives in large numbers, often sold to railways in matched sets that could be operated together under the control of a single crew. These locomotives were designed for maintainability, with major components such as engines, generators, and traction motors, built as units that could be removed and replaced quickly, then repaired in workshops, while the locomotive returned to service with replacement components. American railways discovered they could eliminate the vast infrastructure of roundhouses, coaling towers, water columns, and ash pits, reducing their fixed assets and focusing resources on track maintenance and operations. Britain's railways approached the transition more gradually, influenced by different economic conditions and the nationalisation of the railways in 1948. British Railways, the unified state-owned system, initially attempted to develop a new generation of standardised steam locomotives incorporating the best features of pre-nationalisation designs. These standard locomotives, built through the 1950s, were excellent machines representing the culmination of British steam practice, but they entered service at precisely the moment when the economic case for steam was collapsing. By the late 1950s, British Railways had committed to wholesale elimination of steam traction, and the last steam locomotive was withdrawn from normal service in 1968, just 15 years after construction of standard locomotives had begun. Electric railways expanded their networks where traffic density justified the infrastructure investment. The main lines radiating from major cities were often electrified, allowing for fast, frequent passenger services and efficient freight operations. Electric multiple units, where passenger carriages carried their own motors rather than being hauled by separate locomotives, became standard for suburban and regional passenger services. These trains could accelerate and decelerate rapidly, making them ideal for services with frequent stops, and they could be operated by a single driver controlling the entire train from the leading cab. The smoothness and quietness of electric traction made for pleasant passenger experiences, and the absence of exhaust emissions meant stations and tunnels remained clean. France developed high-speed electric trains that demonstrated the continuing potential of railway transport in an era of growing automobile ownership and air travel. The SNCF, French National Railways, electrified its main lines and developed locomotives and trains capable of sustained high-speed running. By the 1967, experimental runs had achieved speeds exceeding 200 miles per hour, and engineers were designing dedicated high-speed lines where trains could operate far faster than on conventional railways shared with slower freight traffic. The Shinkansen in Japan, opened in 1964 between Tokyo and Osaka, proved that purpose-built high-speed railways could attract massive passenger traffic and operate profitably. These bullet trains ran at speeds up to 130 miles per hour on tracks built specifically for high-speed passenger service, with no level crossings and full-grade separation from all other traffic. Freight railways in many countries consolidated their operations around increasingly long and heavy trains hauled by multiple diesel locomotives, working in multiple unit control. A single crew could control several locomotives distributed through a train, providing immense hauling capacity while maintaining the operational simplicity of a single train. These freight trains grew to lengths that would have been unimaginable in the steam era, sometimes stretching for miles with hundreds of wagons carrying thousands of tons of cargo. The economics of such operations were compelling, with the per-ton cost of transport falling as train weights increased, though the operating complexities of managing such long trains required careful attention to braking systems, locomotive distribution, and train handling. The elimination of steam locomotives from regular service was celebrated by some as progress, and mourned by others as the loss of a familiar and characterful technology. Steam locomotives had been part of the landscape for over a century, their whistles and exhaust beats part of the ambient sound of industrial society, their appearances and mechanical details familiar even to people who never worked with them directly. The transition to diesel and electric traction was undeniably more efficient and economical, but it removed something tangible and comprehensible, replacing it with technology that was hidden inside anonymous boxes. A steam locomotive's workings were visible and understandable, its operation following principles that anyone could grasp, while a diesel-electric locomotive's internal combustion engines, generators, and electrical systems were concealed and required specialized knowledge to comprehend. Yet the practical advantages were overwhelming, and by the 1970s, steam had largely vanished from the world's major railway systems, preserved primarily on heritage railways operated by enthusiasts, determined to maintain these machines in working order for future generations. The final decades of the 20th century saw railways evolve from traditional operations into sophisticated high-technology transport systems. The development of high-speed rail networks represented the most visible transformation, but equally significant changes occurred in signalling, train control, and operational management. Railways that had seemed threatened by competition from automobiles and aircraft discovered they could compete effectively by offering services that matched or exceeded the convenience and speed of alternative transport modes, particularly for journeys of intermediate distance where high-speed trains could deliver passengers from city centre to city centre faster than air travel when airport access and security procedures were considered. The French TGV, or Train à grande vitesse, exemplified this new generation of high-speed railways. The first line, opened in 1981 between Paris and Lyon, featured purpose-built tracks designed for speeds up to 170 miles per hour, with very gentle curves, slight gradients, and complete grade separation. The trains themselves were radically different from conventional locomotives and carriages, being articulated sets where adjacent carriages shared bogies, reducing weight and improving stability at high speed. Power cars at each end of the set contained electric motors and transformers, drawing current from overhead lines and distributing power to motors mounted throughout the train. The aerodynamic shaping of the trains, with smooth noses and sealed bodies, minimized air resistance and allowed sustained operation at speeds where air drag became the dominant force resisting motion. The success of the TGV inspired similar developments in other countries. Spain built an extensive network of high-speed lines connecting Madrid with other major cities, using trains that could operate at speeds exceeding 180 miles per hour. Germany developed the ICE, Intercity Express, with trains capable of similar speeds on upgraded conventional lines and new purpose-built routes. Italy modernised its railways with Frecciarossa and other high-speed services connecting the major cities of the north with Rome and beyond. Even Britain, which had initially dismissed high-speed rail as unsuitable for its relatively compact geography, eventually built the high-speed One Line connecting London with the Channel Tunnel, allowing international services to Brussels and Paris. Japan continued to expand its Shinkansen network, adding routes that connected most major cities on the main islands and developing trains that could operate at increasingly high speeds, despite the challenging terrain of mountainous island geography. The engineering required for these railways was formidable, with extensive tunnelling through mountains and elevated viaducts spanning valleys, but the traffic densities achieved justified the enormous capital investments. The Shinkansen maintained an extraordinary safety record, with no passenger fatalities due to train accidents in decades of high-speed operation, demonstrating that with proper design and operational discipline, very high-speed railway operation could be made remarkably safe. Freight railways underwent their own revolution through containerization and intermodal transport. The standardized shipping container, developed in the 1950s and 60s primarily for ocean transport, proved equally valuable for land transport. Containers could be transferred efficiently between ships, trains and trucks, creating seamless transport chains where goods remained in the same container from origin to destination. Railways developed specialized container trains with flat wagons designed to carry stacked containers, creating services that could compete effectively with long-distance trucking by offering lower costs for large volumes while maintaining reasonable transit times. Double-stack container trains, where containers were stacked too high, appeared on North American railways where generous loading gauges permitted such operations, achieving remarkable efficiency in moving international trade inland from ports. Signalling systems evolved from mechanical and electromechanical equipment to electronic and computer-based control. Traditional signal boxes with their frames of levers gave way to control centres where operators managed large sections of railway using computerized displays and controls. The signals themselves often became less prominent or disappeared entirely, replaced by cab signalling systems that displayed speed limits and movement authority directly to locomotive drivers inside the cab. Automatic train protection systems could intervene if a driver failed to respond to a restrictive signal or speed limit, applying brakes automatically to prevent accidents. These systems made railways safer while allowing for more intensive use of the network by reducing the spacing required between trains. Communications-based train control represented an even more advanced approach, replacing trackside signals entirely with continuous wireless communication between trains and control centres. Trains knew their precise location through GPS and onboard sensors, received movement authority and speed limits via data radio, and could operate with minimal spacing under computer control. These systems promised to dramatically increase railway capacity by allowing trains to follow each other more closely than was possible with traditional signalling based on fixed blocks and trackside signals. Implementation was complex and expensive, requiring extensive testing to ensure safety, but several metro systems and some mainline railways began adopting these technologies. Tilting trains offered another approach to improving journey times without building entirely new railway lines. These trains featured suspension systems that allowed the carriages to tilt as the train negotiated curves, counteracting the centrifugal force that would otherwise push passengers sideways. By tilting into curves, these trains could traverse existing lines at higher speeds than conventional trains without causing passenger discomfort or exceeding safe limits of wheel and track forces. Italy's Pendolino trains pioneered commercial tilting train service, and the technology was subsequently adopted in various forms by railways in Sweden, Spain, Britain, and elsewhere. The experience of riding a tilting train could be disconcerting for passengers unused to the motion, as the train would lean into curves while the scenery outside remained stubbornly vertical, creating a momentary disconnect between visual and vestibular senses. Environmental concerns began to influence railway development as awareness of climate change and air pollution grew. Railways, already more energy efficient than road or air transport for most applications, promoted themselves as environmentally friendly alternatives. Electric railways powered by renewable energy could offer truly low-carbon transport, and even diesel railways produced lower emissions per passenger mile or ton-mile than equivalent road transport. Governments in many countries began investing in railway infrastructure as part of broader environmental policies, reversing decades of relative neglect and prioritising railway development over highway expansion. The railway, which had seemed threatened and outdated in the mid-20th century, entered the 21st century with renewed relevance as a sustainable transport mode capable of moving large numbers of people and vast quantities of goods with relatively modest environmental impact. As the 21st century progressed, railways continued to evolve in ways that would have astonished the pioneers who built the first locomotives nearly 2 centuries earlier. The fundamental principle remained unchanged: guided vehicles running on fixed rails, but almost every other aspect had been transformed by advances in materials, electronics, and understanding of engineering systems. Modern high-speed trains bore little resemblance to their steam-powered ancestors, yet they traced their lineage directly back to those early experiments with steam power and iron rails, representing not a departure from railway tradition, but rather its logical continuation and refinement. Magnetic levitation represented perhaps the most radical departure from conventional railway technology, abandoning the wheel-rail interface entirely in favour of magnetic suspension and propulsion. Maglev trains floated above their guideways, held aloft by powerful electromagnets, and were propelled by linear motors that created magnetic fields pulling the train forward. Without physical contact between vehicle and guideway, maglev trains could potentially operate at very high speeds without the limitations imposed by wheel-rail friction and adhesion. Japan developed the Chuo Shinkansen maglev line, designed to connect Tokyo with Osaka at speeds exceeding 300 miles per hour, while China built shorter maglev lines, including one connecting Shanghai with its airport. The technology was impressive, but extremely expensive, and the inability to share infrastructure with conventional trains limited its application to routes where the traffic volumes could justify dedicated guideways built specifically for maglev operation. Autonomous train operation, already common on metro systems in controlled environments, began expanding to mainline railways. Automation offered several potential benefits, including precise speed control for energy efficiency, optimal use of network capacity through computer coordination of multiple trains, and reduced labour costs by eliminating or reducing crew requirements. However, the complexity of mainline railway operations, with mixed traffic of different train types and speeds, shared infrastructure, and the need to respond to unexpected situations, made full automation challenging. Most automated systems operated with some level of human supervision, with onboard staff able to intervene if necessary and control centres monitoring operations remotely. The psychological and social aspects of automation proved as challenging as the technical aspects, with questions about employment, safety responsibilities, and public acceptance requiring careful consideration. Battery electric and hydrogen fuel cell trains emerged as alternatives to diesel power for routes where full electrification was economically impractical. Battery trains could draw power from electrified sections of line to charge their batteries, then operate independently on non-electrified sections, effectively extending the reach of electrified networks without requiring complete infrastructure along branch lines. Hydrogen fuel cell trains converted hydrogen into electricity through an electrochemical process, with only water vapour as a byproduct, offering zero-emission operation on non-electrified lines. Germany introduced hydrogen trains on regional services, while Britain and other countries tested battery and hydrogen technologies as potential solutions for eliminating diesel traction without the enormous cost of comprehensive electrification. Urban and regional railways experienced a renaissance as cities sought to address congestion and air quality problems. Light rail systems, modern descendants of the electric streetcars of earlier eras, appeared in cities that had abandoned their tramways decades earlier. These systems offered flexible transport capacity between heavy metro systems and bus networks, operating on segregated rights-of-way where possible, but capable of running on street trackage when necessary. The return of trams to city streets, after their widespread removal in the mid-20th century, reflected changed attitudes about urban transport, and the recognition that railways, with their fixed routes and high capacity, could anchor sustainable urban development in ways that automobile-dependent sprawl could not. Freight railways adapted to changing patterns of global trade and manufacturing. Intermodal traffic continued to grow, with containers moving in vast quantities between ports and inland distribution centres. Some railways developed specialised services for automobile transport, consumer goods, and perishable products requiring temperature control. The unit train, carrying a single commodity such as coal or grain from a single origin to a single destination, became common for bulk commodities. These trains operated like conveyor belts, running back and forth between loading and unloading facilities, maximising efficiency by eliminating switching and marshalling operations. Automation began appearing in freight operations as well, with remote-controlled locomotives shunting in yards and systems that could optimise train makeup and routing to minimise empty wagon movements and maximise network utilisation. The preservation of historic railways and locomotives became an important cultural activity, with hundreds of heritage railways operating in countries around the world. These railways, often operated by volunteer organisations on routes abandoned by commercial operators, maintained steam locomotives and vintage rolling stock in working order, offering passengers the experience of railway travel as it had been decades or even a century earlier. The heritage railway movement preserved not only equipment, but also skills and knowledge that would otherwise have been lost as the last generation of steam railway workers aged and retired. These railways served educational purposes, reminding contemporary society of the technological achievements of earlier eras and the central role railways had played in industrial development. Research into future railway technologies continued, exploring concepts that might seem fantastical but were grounded in engineering possibility. Vacuum tube transport, where trains would run in evacuated tunnels at extremely high speeds with minimal air resistance, was proposed for intercontinental routes, though the practical and economic challenges were formidable. Advanced materials, including carbon fibre composites and specialised alloys, offered potential for lighter, stronger railway vehicles and infrastructure. Artificial intelligence and machine learning were being applied to predictive maintenance, allowing components to be repaired or replaced before failure based on subtle indicators of wear or degradation that human inspectors might miss. The railway, after 2 centuries of continuous evolution, remained central to the transport systems of most developed and developing nations. The technology had adapted repeatedly to changing circumstances, incorporating new power sources, new materials, new control systems, and new operational practices, while retaining the fundamental advantages that had made railways successful from the beginning: the ability to move large numbers of people and vast quantities of goods efficiently over fixed routes. The future would undoubtedly bring further changes, perhaps as dramatic as the transitions from steam to diesel and electric power, or from mechanical to electronic control systems. Yet the railway itself, the concept of guided vehicles on fixed rails, had proven remarkably durable and adaptable, and seemed likely to remain an essential element of transport infrastructure for the foreseeable future. As dusk settled over the railway lines stretching across continents, as trains continued their journeys through the gathering darkness, they carried forward a tradition established by those first tentative experiments with steam power, a tradition of innovation, adaptation, and service that had transformed the world and would continue shaping it for generations yet to come.